Hi, I'm Tejaswi Koduru and my partner is Edward Zhang, and we're both from TJH-SST. Our science fair project is detecting erythema migrans rashes via deep learning. Lyme disease is the most common tick-borne disease in the US. In approximately 80% of cases, a bullseye-shaped rash called erythema migrans, or EM, marks the site of infection. The image on the right is a traditional EM rash. Lyme disease is diagnosed through the identification of this rash. However, diagnosis of this rash remains a challenge. In one study, clinicians correctly identified EM rashes only 64% of the time. This inherent difficulty in diagnosing EM rashes highlights the need for new tools to assist clinicians when diagnosing these rashes. Deep convolutional neural networks, or DCNNs, are a subset of deep learning which present a promising solution to this problem. DCNNs are solutions to a wide variety of problems in the medical field. The use of DCNNs in the diagnosis of EM rashes has been investigated before, but these studies focus on the creation of the algorithm rather than its implementation. We aim to create a DCNN capable of binary classification of EM versus non-EM rashes in skin images. Non-EM rashes include images of not only normal skin, but also confounding rashes such as fixed drug reactions.
The lack of a publicly available dataset of EM rashes posed the first challenge in the creation of the DCNN. To create a database of rash images, we first created a Python-based web scraper. This web scraper was given a set of keywords including erythema migrans and bullseye rash. Using these keywords, the web scraper downloaded the images from Google Images. And then we formed an initial database of 1,194 images. Machine-based removal of duplicate images was then performed, and finally the dataset was curated by a clinician. The resulting dataset consisted of 683 images. Before training the model, we split our data into training and validation sets, and applied data augmentation techniques. Images were rotated and flipped to generate more data. We then used deep learning frameworks such as TensorFlow and Keras alongside transfer learning. We experimented with 3 pre-trained DCNNs, including ResNet 50, NASNet Large, and MobileNet. We used the loss optimizer Atom to train our deep convolutional neural networks, and during training we also used an early stopping approach which would stop the training process after 20 epochs if the validation accuracy failed to improve. Additionally, we added a dynamic learning rate scheduler for improved accuracy. Now on to implementation. We converted the trained model into a format that could be stored locally on a mobile device, allowing users to diagnose rashes without a stable internet connection. We then utilized post-training quantization, also known as PTQ, specifically dynamic range quantization, to decrease the size of the model while simultaneously retaining the accuracy. Using this file, we then created both a web and app implementation which uses this model. Here are the results. We chose the ResNet 50 model because it had the highest overall accuracy. Figure 1 plots the training and validation accuracy of the ResNet 50 model. The model had a peak training accuracy of about 92% and a peak validation accuracy of 95%, overall stabilizing at around 93%. Figure 2 shows the AUC value of the model. AUC is a measure of the ability of a classifier to distinguish between classes. Our model has a maximum AUC of approximately 0.95, which is considered excellent by medical standards. The validation and training loss of the model is shown in Figure 3. Both the validation and training loss of the model fell to around 0.25. On the confusion matrix, accuracy of the model was 91.95% and the Matthews correlation coefficient was 0.8391. These results show that the model matches or outperforms clinicians when diagnosing EM rashes. Next, figures 4 and 5 show the app implementation of the model. The 2 buttons at the top allow users to either take a photo of the rashes in the camera or upload an image from the gallery. After selecting an image, the TF-Lite model classifies the image. Results are then displayed at the bottom as percentages. We are currently working on ways to improve the user experience and the accuracy of the model within the device. Figure 6 shows the web tool being used to diagnose EM rashes. There is an upload button where you can upload pictures of rashes, and then the predictions are outputted on the right hand side.
This study yielded promising results for the implementation of machine learning models into a mobile app for the early diagnosis of Lyme disease. Results indicated that the model has a high accuracy when diagnosing between EM and confounding rashes. Out of the 3 models we trained, which include ResNet 50, MobileNet, and NASNet Large, we chose the ResNet 50 model to be used in the app and web tool as it had the highest accuracy and lowest loss. The ResNet 50 model was also chosen due to its high AUC, which was 0.95. For reference, an AUC over 0.9 is considered excellent. These are some of our references. Thank you so much for listening. Hi, I'm Tejaswi Koduru and my partner is Edward Zhang, and we're both from TJH-SST. Our science fair project is detecting erythema migrans rashes via deep learning. Accuracy almost always exceeded the training accuracy in the ResNet 50 model. We believe that this was caused due to our use of a dropout of 0.5. By doing this, we prevented the model from overfitting on the training set. Finally, the last challenge we faced was how to implement the DCNN into the mobile app without sacrificing too much accuracy. Overall, our primary research goal in this study was met. Our results show that our DCNN is highly accurate when diagnosing between EM and non-EM rashes. Our app could have many uses in the medical field. For example, patients could be pre-screened by our app prior to seeing a clinician. While future research into the field is necessary, this study and other similar studies lay the groundwork for the use of machine learning in Lyme disease diagnosis. These are some of our references. Thank you so much for listening.